Hey, hello, Integrated Science. This is Mr. B, and we're continuing on with Section 2 of stars. We talked about measuring the distance with the parallax in the last section. For this section, we're going to get things a little bit easier to wrap your head around, is how we categorize stars. So stars are categorized or classified, put into groups based off of their color, their size, and their brightness. Um, Other important properties include their chemical composition, so what elements make them up, and their mass, so how much space do they occupy. Um, and then the elements aspect can be a little bit not the greatest method because most stars have a chemical makeup that is similar to our sun with hydrogen and helium together. Oh, excuse me. Making up 96 to almost 99.9% of the star's actual mass. So that is, again, majority of stars composed of hydrogen and helium. Um, but for the first thing, color and temperature are directly related to one another because a star's color will in fact indicate the temperature of its surface. The hottest stars, which this would probably be a little section you need to write down, that hottest stars will in fact be blue, and their surface temperatures can be above 30,000 Kelvin. Um, and then the next kind of section there, the surfaces, which is the photosphere. Remember, layers of the sun applies to layers of other stars as well. The photosphere of relatively cool red stars, again, it's still a toasty 3,000 kelvins or so. Um, and then stars with surface temperature between 5,000 and 6,000 Kelvin appear yellow like the sun. So they kind of went in the weird order doing this, but the hottest stars are blue. Second hottest stars would kind of be a more yellowish color like our sun, to where the coolest stars would appear red, with temperatures again between 3,000 Kelvin or so. And they kind of give an example of three stars that are visible. We have what are called Betelgeuse, Procyon, or Procyon, I believe, and Sirius are three of the brightest stars in the sky. Again, right there, right there, right there. Um, and Betelgeuse is much cooler than the others, and you can tell this because these two stars over here, we have a blue star. Remember, blue is the hottest, and we have Betelgeuse over here, which is more of a yellowish color. So it's going to be cooler than the ones that are kind of in that blue range there. So color can determine what the temperature of the stars actually are. Again, blue, yellow, red, kind of being our from hottest to coldest there. And then kind of something similar to color, but not necessarily the same as brightness, because well, whether how bright something is will maybe help you determine what its color is. But astronomers have discovered that the brightness of stars can vary by a factor of more than a billion, so it's kind of hard to determine the brightness because of the fact that stars that look bright may actually be farther away than stars that appear dim. It's really hard to tell with brightness because there's two different types of brightness depending on how far away you actually are from an object compared to what it actually is producing. So for the example that they give is that these streetlights all have about the same absolute brightness. Like they're all generating the same amount of light. However, the closer lights appear brighter simply from the essence that you are closer to them. So that means that it has what's going to be a different apparent brightness, which I think they talk about right here. So our sun obviously appears very bright to us because it is much, much closer than other stars. Again, the next closest star is 4.3 light years away, so very far away. So the brightness of a star as it appears from Earth is called its apparent brightness. So again, if I ask you which star has the greatest apparent brightness, um, you would say the sun because it is in fact closest to the Earth. So as you get farther away, your apparent brightness is going to decrease. So again, as distance increases, the apparent brightness is going to decrease because you're farther away, so it's just going to appear more dim. That doesn't mean the star itself is actually any more. It doesn't mean the star is dimmer. Again, there's going to be plenty of stars out there that are much brighter than the sun, but again, the sun is the one closest to us, so that is the one that appears to be the most bright to us. Um, so kind of the more accurate measure of how bright a star really is or how bright a star actually is called its absolute brightness. Um, its absolute brightness is a characteristic of the star that does not depend on how far it is from Earth. Again, it is what it is. It's absolute. It's how bright it actually is. Um, you can, in fact, calculate a star's absolute brightness if you can know its distance from Earth and its apparent brightness, so that we can figure out, okay, it's this far away and this is its apparent brightness, so it actually is going to be generating a brightness, an absolute brightness closer to this. Because like I said, there's probably many more out there that have a absolute brightness higher than the sun, but again, um, the apparent brightness is why the sun appears to be the brightest to us. So then after, again, another classification after temperature, after absolute brightness, we have the size and the mass. So if we know its temperature and we know its absolute brightness, we can estimate its diameter and then calculate its volume based off of that. The masses of many stars can be determined by observing the gravitational interaction of stars that can occur in pairs. Again, we can see how sometimes they kind of almost might rotate around one another and see the interactions they have with objects around them to determine how large they actually are. For most stars, there is a relationship between mass and absolute brightness, so the size will affect its absolute brightness. And then, so composition, we have a tool called a spectrograph, which is an instrument that spreads light from a hot glowing object into what's called a spectrum. A spectrum is just spreading out the colors of the rainbow. I think we've talked about this before, how the colors of white light and then the colors of light that we observe can actually be spread apart into all the different colors of the rainbow based off of different wavelengths. If we haven't talked about that, I know you'll talk about it next year, but again, we'll see a picture of that here in a second. Astronomers can use spectrographs to identify the various elements that are in a star's atmosphere. So this right here is a spectrum. Again, we have the colors of the rainbow. We have red, orange, yellow, green, kind of turns into blue, indigo, violet down here at this end, the colors of the rainbow. There's these different lines showing that different colors have been absorbed. These are called absorption lines, and different elements will absorb different colors. So these lines, again, this line right here means there is an element present in this star that is absorbing this color light, and an element that's absorbing that color light. So using this spectrum, the spectrograph, it can tell us which kind of elements are present there, which is just explained right here. So the elements within a star's atmosphere absorb light from the star's photosphere or the star's surface. Each element will absorb light of different wavelengths. So again, all the reason, again, that white visible light that we see is actually made up of all the colors of the rainbow that exist at different wavelengths. So different elements will absorb different wavelengths of light. A star's bright spectrum has a set of dark lines called absorption lines that show where light has been absorbed. So again, right here, absorption line, absorption line, absorption line. They're everywhere. Again, this is a broken up spectrum showing that there's elements, again, the darker lines probably being the more prominent elements, showing which elements are present in that star. They can be used, again, to identify different elements in the star. Absorption lines of most elements have been identified in the spectra of stars. Observation of such lines in many stars have shown that the composition of most stars is in fact fairly similar. So by using these spectrographs, again, we're not going to continue, or we're going to keep using them because they are in fact kind of confirming our data. We always have to confirm our data that stars are mostly composed of the same thing. Again, mostly hydrogen and helium, and then again, maybe someday we'll make a discovery of star with different composition, but it seems like that's probably not going to be the case. So that is it for this video. Let me know if you have any questions.